When we start talking about greatest common factor, we have to think differently than we do when we're thinking least common denominator, but the procedures are similar, but the rules will be different for you, so I want you to separate those in your mind. Greatest common factor is the greatest factor that several terms or two terms have in common. We'll start off with the same process we did for least common denominator. We start with factoring to primes. So for the example 136, we'll factor it to primes. We would end up with, well, let's start with 4 times 9. Those are two of the factors I remember easily. And then I would factor 4 into 2 times 2, and there's 2 primes. And I'd factor my 9 into 3 times 3, and those are all primes. So I can say 36 is equal to 2 times 2 times 3 times 3. 90, I'd probably say 9 times 10. And then I'd factor 9 again into 3 times 3. Both of those are primes. And then I'd factor 10 into 2 times 5. And both of those are prime. So 90 is 2 times 3 times 3 times 5. Now what we're looking for is all of the factors that they have in common. Well, I have a 2 in 36 and I have a 2 in 90. I have a 3. I have 2 3s in 36 and I have 2 3s in 90. And that's all that they have in common. That extra 2 and the 5 in 90, they don't both have them, so I can't use them. My greatest common factor then, I would take the ones they have in common, 2 times 3 times 3, which is 18. The greatest thing that will evenly divide into both of these numbers is the number 18. Let's look at example 2. We've got 3 numbers to deal with. When we say 30 and we factor 30 to primes, we'd say 3 times 10. And then we'll do 10 again, 2 times 5. 30 is equal to 2 times 3 times 5. 75, well, I'd probably say 3 times 25. And then 25 would factor into 5 times 5. 75 is equal to 3 times 5 times 5. Now I've got a third number. So for our greatest common factor, all 3 of these numbers have to have the factors in common. 135 is not as easy for me to factor. I know 5 goes into it, and then I would have to divide. Once I divide, I find out that the number I'm looking for is 27. It's not prime. It'll factor again into 3 times 9. 3 is prime, but 9 will factor again into 3 times 3. So 135 is really 3 times 3 times 3 times 5. Now, what do they have in common? Well, I have 1 3 in 30, 1 3 in 75, and I can use 1 3 and 135. And then I do have a 5 common to each of them, 1 5, and that's it. The other numbers I haven't circled are not in all 3 of these factorizations. So greatest common factor is going to equal the numbers I've circled, 3 times 5, or 15. And that's the greatest number that I could evenly divide all 3 of those numbers by. Example 3, what about exponents of variables? We have to think. If x cubed is primed, I would write it as x times x times x. X squared, I would write it as x times x. And x to the power of 5, I would write x times x times x times x times x. How many do they have in common? Well, they've all got x's, but the only thing that they can all have in common is just 2 x's. The rest of them do not exist in all 3 factorizations. So what I really find is my greatest common factor when I'm dealing with exponents is the term that has the smallest exponent. So I don't really have to factor those to primes. I just have to remember the smallest exponent that they all have, is the one they have in common. Let's look at example 4. We're not going to factor these. We're just going to follow that rule. The p variable, p to the 7th, p to the 8th, p to the 9th. The smallest exponent, p to the 7th. My greatest common factor is going to have p to the 7th in it. What about the q? I have q to the power of 1, q to the power of 1, and q to the power of 3. Well, the smallest one I have is q to the power of 1, which I really don't have to write that exponent. So my greatest common factor is p to the 7th times q. Let's combine variables and coefficients now in example 5. First, I've got the coefficient 32, which I know I can factor into 4 times 8, and then I can factor the 4 again, 2 times 2, I can factor the 8 into 2 times 4. And I factor that 4 again, 2 times 2. Well, I have a lot of 2's. Actually, 32 is 5 2's. What about 18? Well, 2 times 9. And then 9 is 3 times 3. Now, I don't have room to write these out linear, but can't you just see that the only thing they really have in common is 1, 2? So the greatest common factor is the coefficient is going to be 2, and then I want the variable, the smallest exponent, x to the 5th, x squared, is going to be x squared. So my greatest common factor for 32x to the 5th and 18x squared is 2x squared. That's the greatest number they both have in common. Let's look at example 6. One of these numbers is negative and one's not. Well, they don't have the negative in common, so we're not going to worry about that. But what number would 21 and 14 have in common? I think you can see that it would be the number 7. You could factor it to primes, but sometimes you can just see it. Then look at the variable, x cubed and x. And of course, the smallest exponent is x. So they both have 7x in common. That's our greatest common factor. For example 7, we're going to do this with 3 different terms. We're looking at coefficients first, 7, negative 21, and 14. The common factor is 7 for the x variables, x cubed, x squared, and x. Lowest exponent is just x. And for the y variable, y cubed, y squared, y to the 4th, the lowest exponent is y squared. So our greatest common factor is 7xy squared.